Hello and welcome to 10.2, Plane Curves and Parametric Equations. A parametric equation is an equation where the x and y coordinates are expressed as a function of another parameter, typically t. It doesn't have to be a t, it could be a theta or something else. Definition of a plane curve: if f and g are continuous functions of t on the interval I, then the equations x equals f of t and y equals g of t are called parametric equations, and t is called the parameter. The set of points x, y obtained as t varies over the interval I is called the graph of the parametric equations. Taken together, the parametric equations on the graph are called a plane curve, denoted by C. Orientation of the curve. That's the direction the curve is traced when plotting points in order of increasing values of t. With example 1 here. Sketch the curve represented by the parametric equations, indicate the orientation of the curve, and write the corresponding rectangular equation by eliminating the parameter. So we have x equals 3t minus 1 and y equals 2t plus 1. So let's go negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. 3 times negative 5 minus 1 is negative 16. 3 times negative 4 is negative 12 minus 1 is negative 13. Obviously, you start seeing a pattern yet. 3 times negative 3 is negative 9 minus 1 is negative 10. So it's going up by 3 every time, as you might expect. So that would be negative 7, negative 4, negative 1, 2, 5, 8, 11, and 14. Let's look at the y one. 2 times negative 5 is negative 10 plus 1 is negative 9. 2 times negative 4 is negative 8. Plus 1 is negative 7. 2 times negative 3 is negative 6. Plus 1 is negative 5. So these are going up by 2 every time. So negative 3, negative 1, 1, 3, 5. Make sure I'm lining it up correctly. 5 goes here. Then 7, 9, and 11. Now our graph only goes from negative 6 to 6 in both directions, so let's just plan on graphing between negative 7 up to that. Okay, so let's start with negative 7, negative 3. So now we're not even going to worry about the t values so much. Negative 7, negative 3. Negative 7, negative 3 would be about there. Then negative 4, negative 1. Then negative 1, 1. And then 2, 3. 5, 5. 8, 7. Something right about there. And this is the direction it's going in. As t gets bigger, it's going that direction. Now the next part of this set, you eliminate the parameter. So if we have x equals 3t minus 1, if we add 1 to both sides, x plus 1 equals 3t. If we divide by 3, t would be x plus 1 over 3. And we could take this expression and put it in terms of t there. y equals 2 times x plus 1 over 3 plus 1. So y equals 2/3 x plus 2/3 plus 1, or y equals 2/3 x plus 5/3. And that would be it. Okay, I'm going to scroll up a little bit here. It says eliminating the parameter, solve for t in one equation. We did it for the x. Substitute into the second equation. We substitute into the y. And simplify the resulting rectangular equation. Okay, I'm going to move on to the next page. Feel free to pause. Example 2 says use a graphing utility to graph the curve represented by the parametric equations. Indicate the orientation of the curve, same thing as before. Then eliminate the parameter and write the corresponding rectangular equation. Well, excuse me. Let's just go and look at that parameter right off. We know that's sine squared theta plus cosine squared theta equals 1. And look at these are in terms of the parameter theta, by the way. So that's sine squared of 2 theta plus cosine squared of 2 theta would be equal to 1. Now, x equals 4 sine 2 theta. So x over 4 equals sine 2 theta. And y equals 2 cosine theta. So y over 2 would be cosine 2 theta. So we can write this as x over 4 squared plus y over 2 squared equals 1. That's x squared over 16 plus y squared over 4 equals 1. And we have an ellipse. Oh, you could graph this, the graphing utility, that's right. Your graphing calculator. You would put it in parametric form under the form or the mode. You don't want it in function or polar, you want it in parametric. Okay, so this is an ellipse. Major axis is going to be the x part, goes to the origin. So square root of 16 is 4. Square root of 4 is 2. That's it. Okay, moving on to example 3. Again, pause if you want. Determine any differences between the curves of the parametric equations. Are the graphs the same? Are the orientations the same? Are the curves smooth? So let me scroll up a little bit more. So we have both the curves on one screen. Actually, is there a C to this? There is a C and a D. So we'll start with these two, then we'll go to the next page. So here we have x equals t, y equals 2t plus 1. If we put x in place of the t, y equals 2x plus 1. So slope is 2. That's the direction. That's going to go forever. Coming from down below, up forever. In this next case, x equals cosine theta and y equals 2 cosine theta plus 1. Now, cosine theta is going to produce values between -1 and 1. Therefore, if I were to substitute this in here, I'd have y equals 2x plus 1. But we can only go for x being between -1 and 1. So y equals 2 times negative 1 plus 1, that's going to be negative 1. Y equals 2 times 1 plus 1, that's going to be 3. So we go negative 1, and then 1, 3. So it's going to go just between those values. And it's going to go up that way, it's going to come back down, go back up, come back down, it's just going to oscillate there. Go on to the next page. I should do this. Our derivative with respect to theta, derivative of x with respect to theta is going to be negative sine theta. And the derivative of y with respect to theta is going to be negative 2 sine theta. So these are both 0. When theta equals 0, plus or minus pi, plus or minus 2 pi, and so on. Owing to the smoothness of the curve. Okay, next one, x equals e to the t, e to the negative t, and this should say y equals 2e to the negative t plus 1. So in this case, again, if you substitute this in there, you have y equals 2x plus 1, but e to the negative t is always going to be greater than 0. So it's only going to be the positive values. And the bigger t is, the smaller e to the negative t is. So this is going to have the intercept here at 1 again. It'll never be negative, but it's going to be coming this direction. Because, again, as t gets bigger, e to the negative t becomes smaller. In the last case, x equals e to the t, y equals 2t e to the t, so y would be 2x plus 1. This will also only be positives. It goes that direction now because as t gets bigger, e to the t gets bigger. So all these are related graphs, very similar, but they have different characteristics to them. Oh, and dx dt is going to be equal to e to the t, which is never 0. And dy dt is going to be 2e to the t, which is never 0. So no points to exclude there. Or I should say there's no points where you're going to have a 0 derivative, which means it's always going to be increasing. Okay, moving on to example 4. Eliminate the parameter and obtain the standard form of the rectangular equation. So circle x equals h plus r cosine theta, y equals k plus r sine theta. Okay, so we subtract the h from both sides, we'd have x minus h equals r cosine theta. And subtracting the k, y minus k equals r sine theta. We can divide by r in both cases. X minus h over r equals cosine theta. Y minus k over r equals sine theta. We know that sine squared theta plus cosine squared theta equals 1. So that, should have done the other way, cosine squared. Anyway, so that x minus h squared over r squared plus y minus k squared over r squared is 1. So x minus h squared plus y minus k squared equals r squared. And maybe for viewing this, we should say cosine squared theta plus sine squared theta equals 1. Addition is commutative, but people might be confused with that. And that's the end of it. So this is using, for example 5, use the results of example 4 to find a set of parametric equations for the conics, the circle with center at 3, 1 and radius 2. So this is your HK, that's the R. So it'd be x equals 3 plus 2 cosine theta, and y equals 1 plus 2 sine theta. That's it. So I'm using these formulas down here. Let's go on to the last page, our last problem. Okay, a smooth curve. We alluded to it a few problems ago, a couple examples ago. Definition of a smooth curve is a curve C is represented by x equals f of t and y equals g of t on an interval. I is called smooth if f prime and g prime are continuous on I and not simultaneously 0. So we had the case where the one curve was simultaneously 0 at 0, pi, 2 pi, and so on, except possibly at the endpoints of I. The curve C is called piecewise smooth if it is smooth on each subinterval of some partition of I. Use a graphing utility to graph, I'll draw you what I got from the graphing utility. To graph the curve represented by the parametric equations, indicate the direction of the curve, identify any points at which the curve is not smooth. So if you were to graph this one, it would look like this. That's the direction it's going in. Looks like waves on the ocean. So if we have x equals theta plus sine theta, dx dt is going to be 1 plus cosine theta. 1 plus cosine theta equals 0. We're going to see where this is 0. Cosine theta equals negative 1. So theta would be pi, 3 pi, 5 pi, and 7 pi, and so on. Our y would be 1 minus cosine theta. dy d theta is going to be sine theta. Sine theta equals 0, where? At theta being 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and so on. So this is not smooth every time there's an odd one. For pi, 3 pi, 5 pi, 7 pi. So not smooth when theta equals 2n minus 1 pi. That generates odd coefficients. And that's that. And that'll do it for this section for 10.2. So, send me your questions and I'll see you guys online. Thanks.